Hello again. Today I'm going to talk about waves. First, a number of definitions, then I'm going to talk about interference of waves, and finally intensity. So what is a wave? A wave is a moving disturbance that carries energy but not mass. So suppose I have a string stretched between two walls, for example, and I pluck that string so that there's a wave that travels down it. So this wave might travel along down the string. So it moves along the string like that. Only the wave travels down. Only the disturbance goes down the string. The string stays behind. So this part of the string, as the wave goes by, this part moves up and then this part moves down, but the string is still there. So the wave is the disturbance that moves along the way. So that's just an example of a wave. So some other definitions, again using a wave on a string as an example. So suppose I have a wave like this. It's moving with some velocity v, and before the wave went by, if you imagine it being on a string, it wouldn't have to be. It could be a wave of water or some other type of wave. Just a number of definitions. This distance, the maximum displacement from equilibrium, is called the amplitude. Amplitude. Maximum displacement from equilibrium. That's the same definition of amplitude as we had for simple harmonic motion, but now we're talking about waves. The distance between adjacent crests is called the wavelength. So from one crest to the next crest is called the wavelength. We usually give it the symbol lowercase lambda from the Greek alphabet, so we'll call that lambda. This was A. This is the distance between adjacent crests. I left the N out of distance. Let's see. Distance between adjacent crests. It wouldn't have to be crests. It could be, from one trough to the next trough, but that distance is called the wavelength. So as the wave goes by, if you, for example, were standing here looking in admiration at this wave, one crest goes by and then another crest goes by, the time between adjacent crests passing a point is called the period. T, time between adjacent crests passing a point. Notice that's similar to the definition of a period of simple harmonic motion. Period of simple harmonic motion was the time for complete oscillation. Now we're talking about the time between crests passing a given point. That's the period of a wave, has units of seconds. The number of crests passing per second is the frequency. Number of crests passing some point. And again, we give it, just like in simple harmonic motion, we give it the unit hertz. Notice that it takes one period for the wave to move one wavelength. So given that distance equals velocity times time, a distance of a wavelength equals the velocity of the wave times a period. period is 1 over frequency, so it's still true. These are related, just like in simple harmonic motion. Period is 1 over frequency, that's still true. So we can multiply by f and get the relation v is lambda f, and that's true for any wave. And that's an equation you should memorize. It's really an important equation. Just a real quick example. Maybe you have a favorite radio station, 101.5 FM. I don't know if that's a radio station, it probably is. But this probably means 101.5 megahertz. That's 101.5 times 10 to the 6th hertz. Radio waves travel at a speed v of 3 times 10 to the 8th meters per second. So the wavelength of the waves carrying that radio signal are v over f is 3 times 10 to the 8th meters per second divided by 101.5 times 10 to the 6th hertz. Now, hertz is 1 over seconds, so this is 1 over seconds over 1 over seconds will be meters. So let's see what that is. 3 times 10 to the 8th, 101.5 times 10 to the 6th. That gives me 2.96 meters would be the wavelength of those waves carrying that FM signal. All right, so that's just some definitions in our introduction to waves. I'm not done, I'm just out of board space. All right. Well, there's more than one kind of wave. There's 2 general classes of wave. The one I've drawn here is called a transverse wave. So a transverse wave is a wave where the particle motion is perpendicular to the velocity. So as this wave goes by, if this is, for example, a string, the string would be going up and down like this as the wave goes that way. So if the wave is going to the right, the string is going up and down perpendicular. That's an example of a transverse wave. The particle motion is perpendicular to the direction of the velocity. Perpendicular to the wave velocity. But there's another class of wave. There's something called a longitudinal wave. This where the particle motion is parallel to the wave velocity. It's a little harder for me to draw, but I think you'll get the gist of it. If you imagine a long slinky, and I send a jolt down that slinky. So suppose I start with just a slinky that's nice and uniform like this. And then I pull it and snap it so that some vibrations go down that slinky. So when I do that, there'll be some parts of the slinky that will press together and some that will stretch apart. So at some instant after I do that, there'll be parts that are compressed and parts that are stretched apart, and parts that are compressed, and parts that are stretched, and parts that are compressed, etc., as this wave moves along this way. So the wave motion is these compressions, or these motions this way, parallel to the wave, so that pushing the slinky together, pulling it apart, pushing it together, so the motions are like this, and the wave is also moving that way. That's a longitudinal wave. That's an example of a longitudinal wave. Another example that we'll spend a whole chapter on, sound is a longitudinal wave. So we'll return to this again in the chapter on sound. So you need to know the difference between a transverse wave. Light, for example, is a transverse wave, even though it's not an actual particle motion. It's made up of electric and magnetic fields. But remember when we talked about electromagnetic waves, we drew them like this. we said the electric field was this way and the magnetic field was that way. So the electric field was oscillating like that, the magnetic field like that, while the wave went that way. So light is a transverse wave. So I call this particle motion. Here it's not really a particle, it's the electric and magnetic fields, but the thing that is oscillating is perpendicular to the direction of the velocity. That's a transverse wave. I just called it particle for simplicity. Okay. All right. Next topic on waves is superposition, or some waves exhibit this important property called superposition. When two or more waves cross the same point at the same time, they add together. That's what superposition means. When two or more, I'll just say two, waves cross, the resulting wave is the sum, try to write that a little clearer, is the sum of the individual waves. In fact, that's an indicator that what you're dealing with is indeed waves. When you study light, you'll see something called Young's experiment that use this to indicate that light is a wave. So for example, there's something called constructive interference. If I have a pulse, which is a type of wave traveling this way on a string, and a pulse traveling the other way, they wouldn't have to be waves on a string. These could be light waves or sound waves. So one's traveling this, like that, one's traveling to the right, one's traveling to the left. When they meet, they'll just add together. So a little bit later, they'll just make a bigger wave, kind of exaggerated here, I guess, and then they go on their merry way. So this pulse that was over here is now over here. This pulse that was over here is now over here. But while they met, they added together. That's called constructive interference, and that's an indication it's a wave. Particles don't do that. Imagine this is a bowling ball and another bowling ball. When bowling balls meet, they don't briefly make a great big bowling ball and then just keep going. But waves do that. When waves meet, they can make a bigger wave and then just pass through each other and keep going. So when they make a bigger wave, that's called constructive interference. So this is where, well, I'll just leave it at that. There's also something called destructive interference. So suppose I have a pulse like this and a pulse like this that meet. This upper one going to the right, the lower one going to the left. When they cross, the result is still the sum, but one of these is positive and one is negative. So when they cross, they essentially cancel each other out. But the energy is still there. And so this wave will continue, an instant later, this wave continues on its way, this wave continues on its way. So an instant later, these have passed through each other and keep going. So destructive, they destroyed each other, but they continue going. So that's another example of superposition or interference. Constructive, when the resulting waves add to form a larger wave. Resulting wave is larger, and the resulting wave is smaller. And by smaller, I mean smaller than either one was individually. And by larger, I mean larger than either was individually. Well, there's a special case of this, of constructive, destructive interference, that turns out to be really important in engineering and in acoustics. And that's the case where you have constructive and destructive interference of an incident wave and a reflected wave. So suppose I have, imagine a wave on a string again, and I send a wave to the right, and it comes down and it hits the connection here and reflects back. And I get constructive and destructive interference between the incident wave and the reflected wave. For certain frequencies, those can add together to produce what's called a standing wave. So for example, the wave might look like this. And now this wave is just standing there doing this. When this one's up, this one's down, and it just does this. That's just an example. There are other patterns of standing waves that you'll see in a video later, but this is an example where we got constructive interference here, destructive here, and the pattern is fixed. This maximum displacement is called an antinode. So this is called a standing wave. This maximum is called an antinode. And this minimum is called a node. We're going to define the standing wave as a wave of fixed nodes and antinodes due to, now I said it was due to an incident and a reflected wave interfering with one another, constructive and destructive interference. I'm getting constructive interference here and destructive there. That's true. But this happens because of something else you've learned about, because of resonance. So this happens at particular frequencies where this is possible. So a standing wave is a wave of fixed nodes and antinodes due to resonance. So this antinode is a point of maximum displacement or motion, I'll call it displacement, in a standing wave. And a node is a point of zero or at least minimum motion in a standing wave. Let's call it zero displacement in a standing wave. So I'm not going to do a lot more with this right now, but in the next chapter on sound, these are going to be really important because the standing waves in, for example, on a guitar string, on a string on a piano, determine the notes that are played in those instruments. Or standing waves in sound in a wind instrument determine the notes that are played in those wind instruments. Okay, last topic for today is intensity. Intensity of a wave. Intensity is the rate at which energy flows through a surface per unit area. Rate, that means you divide by time, at which energy flows through a surface per unit area. So if I've got some surface here, and I've got energy going through that surface, it could be due to sound or light, is presumably in this chapter due to some waves going through that surface. This surface past some area A, and there's energy passing through it. The intensity I is the rate of energy flow, so that's delta E over delta T divided by the area A. But delta E over delta T is power, so that's just power over area. Power has units of watts, area has units of square meter, so we just got intensity is power per unit area in watts per square meter. So it's pretty straightforward, awfully important. This is, for example, how we determine how much energy you can get out of a solar panel, for example, by knowing the intensity of the sunlight falling on it. So for example, suppose I shine a laser on a wall. So there's a laser beam and it hits a wall over here. And let's imagine that this makes a 3 millimeter diameter spot. And this is a 5 milliwatt laser. That's like a laser pointer. Then the intensity in that spot, I, is the power over the area. It's the 5 times 10 to the minus 3 watts over pi times 1.5 times 10 to the minus 3 meters squared. That's just pi r squared, or I divided the diameter in 2. That gives me an intensity of 707 watts per square meter. Now suppose you take the same laser and you take a lens and you focus it down to a really tiny spot. You focus it down to a diameter of, let's say 2 microns, 2 micrometers, which is plausible. You can do that. Now intensity would be power per unit area. It would be 5 times 10 to the minus 3 watts over pi times 1 times 10 to the minus 6 meters squared. That's 1.5 times 10 to the 9 watts per square meter. Where you've just by focusing it, you've now got your intensity 1.5 gigawatts per square meter. All right, so there's our example of intensity. And we'll, of course, practice it in the in-class and in the homework. That's really all for today. That's our introduction to waves. They're awfully important. I'll see you soon.